are going to continue one last little unit before the end of the trimester, and that is Applications of Quadratics. And it's not teaching you anything new, it's having you interpret parts of a quadratic function. So you're going to be getting application problems just like the one listed here. So a frog sitting on the ground, or is sitting on the ground when he is scared by a big dog. The frog jumps at an initial speed of 6 feet per second, and his movement is modeled by the equation h of t equals negative 6t squared plus 6t. So right there's your quadratic function, where h is the frog's height at any given time. So I have a diagram here, quadratic keywords, and this is really just a template for if I'm asked a certain question about this frog's path, what part of the quadratic am I finding? Because you guys know how to do that. You know how to find the x-intercepts. You know how to find the vertex. You know how to find the y-intercept. So none of that's new, okay? The only thing that's new is I'm asked this question, what part of the parabola is that asking me to calculate? So I want to start here at the bottom with our cute little froggy and talk about, okay, the zeros. Remember, zeros is just another name for x-intercepts. And these could be in varying places. They're not necessarily going to be in the two places in this picture, okay? So when you're finding the x-intercepts, you're going to be asked a question such as, when did the frog land back on the ground, right? As a frog hops, like here he would hop and he would go back on the ground. Granted, it's higher in this picture, but that's the general idea. Or how long was the frog in the air? Because that's really the same type of question. So we're going to fill these in these boxes. So it could say, when does the frog hit the ground? And hopefully that's a little, it's not frogger and he goes splat. Hopefully he just reaches the ground safely. Or another way that can be phrased is, how long is the frog in the air? Right, and that can be realistic, right? If frog jumps, it's got to come back to the ground. Since we live on Earth, it's not going to just float in the air forever. So the second zero, so the one here on the left, if it is in the negative, we ignore it, okay? The reason being, if you think about it, this x-axis is, excuse me, this is time. I can't go back in time. So if your leftmost zero is negative, you ignore it because you cannot go back in time. It's still part of the parabola, but won't be part of the interpretation of this frog's trajectory, okay? Sometimes that left side zero will be at the origin. It'll be at 0, 0. And that's fine. We're not going to ignore that one. That means the frog was on the ground at time 0. Okay? So there, if you're asked, when does the frog hit the ground, or how long is the frog in the air, that's asking you for your x-intercepts. So you can, a lot of times you can just look at the graph, or in the next coming days, we'll talk about, well, what if I don't have a graph? What can I do to find those? All right, if we move up a little bit further, we're going to talk about y-intercept. Oops, sorry. So if I have a y-intercept, that is a point 0, some number, okay? Again, the x-axis is time. And so this number here is going to be the height of the frog. So what the y-intercept is going to tell you is at time 0, the frog is this high off the ground. So in this situation with a frog jumping, you know, he's probably not going to start off of the ground. But we can have other examples like you threw a rock off of a bridge, or you threw, basically, I mean, we've got like all kinds of situations where you can throw off of any height that's not with the ground. So this tells you the initial height or the starting height. Like what's the height of your object at time 0? So at the beginning of the launch, how high was it? Okay, so then we have the vertex, and the vertex is really kind of tricky because you've got two parts to it. You have the X value and you have the Y value. And you've got to remember that this X value, this is your axis of symmetry, right? So that is, if I were to draw a line down the middle of this, okay, that's what that is asking. And the X, this is time, versus the Y value is your height. Now, I'm even going to change that Y value a little bit. And instead of just labeling it as height, we know what this vertex, and if we think about it in context of a story problem, it's not going to just necessarily be height, but it's going to be our maximum height. What's the highest that this frog jumped? Okay, or what's the highest that the object went after launching? So for the axis of symmetry, the X value, right, that's time. So that's going to ask you a question such as, how long does it take to reach max height? There's not nearly enough space for me to write that with this diagram, but okay, your X value, the axis of symmetry, would answer how long does it take for that object to reach its maximum height. All right, the last box on this diagram is this one right here, which I kind of cut into. It says how high the object is after an unknown amount of seconds, and I'm just going to say X seconds. What you can do is you're going to plug in a number to the function, or you can interpret it off of the graph for, hey, what is the frog's height after 1 second? What is the frog's height after 2 seconds? Okay, you can plug it into the function or look at the graph for that information, because that's going to really vary on after how many seconds it wants you to apply that. So with all of this, let's do some practice problems. So we have a soccer ball is kicked and follows the trajectory given by h of t equals negative t squared plus 4t, where h represents the height in feet and t represents time in seconds. So one thing that I want to make sure that as I read that question that I understand is that height is in feet and time is in seconds. A lot of time in Algebra 1, we do use feet and seconds, but it could be hours, minutes, or instead of feet, maybe it's yards. Okay, it could be a lot of different things. So we're given the graph, and this is the graph that goes with that equation. So how long is the ball in the air? Well, what part are we being asked to find? What part of that parabola? So the y-axis is height, and the x-axis is time. So from this point here, this is time 0. It is also at height 0. And sometimes you just need to visualize what this parabola would be. It's the ball gets kicked and it goes up in the air, and because we live on Earth, it eventually comes back down, and this is when it hits the ground again, because that's again when it's at height of 0. So how long is it in the air? Well, it went from 0 seconds to 4 seconds, so this would be 4 seconds. Okay, next piece. How high did the ball get? So think about in context of the graph, what part of the parabola would that be? Well, again, you kick the ball, it goes in the air, and we want to know how high does it get? So that's going to be our vertex. And this vertex is at 2, 4. But again, we got to think about, well, which one of those tells me the height of the ball? X is time, and Y is height. So the Y value of this would be the height of the ball. So this would be 4. And if we look back into our problem, height is measured in feet. So this would be 4 feet. Okay. Oops, sorry guys. Question 3, when did the ball reach its maximum height? So again, that's going to be how long did it take to get to the vertex, which is our axis of symmetry, right? Because that x coordinate is time. So this would be 2 seconds. What is the ball's starting height? And we actually already kind of talked about this of at time 0, how far is that ball off the ground, right? Starting height at time 0, or that's our Y-intercept. In this case, it started on the ground at time 0. So this would be 0 feet. And then for question 5, what is the height of the ball after 3 seconds? Now I can either plug in t equals 3 to my function above, or I can follow my graph and say, hey, 3 seconds is right here. What is the height of the ball at 3 seconds? And in this case, it happens to be 3 feet. Okay, and it is height, so that's how I know that it was feet. Okay, we're gonna try one more. All right, so this one, we have a rock is thrown off the top of a piece of playground equipment. Its path is shown from the graph at right. The equation of its path is represented by h of t equals negative t squared plus 4t plus 5, where h of t represents height in feet and t is time in seconds. So again, we're going to kind of just make sure we notate our units. How high was the rock thrown? So we know that is dealing with our vertex. And again, we've got to think about, well, which part of the vertex is it? Is it the x value, which is axis of symmetry, or is it the y value, which is 9? And it would be our y value, that's the height. So this would be 9 feet. Okay, the next question, how long does it take the rock to reach its maximum height? So we're still working with maximum height, so we're still working with the vertex. And now it's just a matter of, well, how long did it take to get there? Well, that's the x value or t value if you're using the equation. So that would be 2 seconds. So the vertex of 2, 9, it takes 2 seconds to get 9 feet off the ground, is what that can be interpreted as. Okay. Oopsie. Okay. Question 8, how tall is the playground equipment? That is another way to phrase what is the initial height of the rock. And initial height is a y-intercept. And if we look at our graph, our y-intercept is 0, 5. So at time 0, it started 5 feet off the ground, which would be how tall the playground equipment is if, just like in the problem, it says a rock is thrown off the top of a piece of a playground equipment. So it's not starting on the ground, it's starting above the ground 5 feet, because at time 0, that graph is 5 feet above the ground. Okay, 9, how long is the rock in the air? Well, that's our X intercepts, right? Now, again, here's a situation where we do have a negative X intercept, and we want to ignore this one because I cannot go back in time. So basically, all of this over here, I ignore, okay? Because I am standing on top of a playground piece of equipment. I throw the rock, it goes in the air, and then it comes back to the ground. So all you're looking at is this X-intercept, and it's at 5, 0. So I threw it at time 0, it landed at time 5, so this would be 5 seconds. Okay. There's all my squiggles, my amazing stick person. Last question is how far off the ground is the rock after 1 second? So I could plug in 1 for all the t's in my equation in the problem, or because I have a graph, I can say, okay, 1 second is right here. How tall is the graph at that point? Follow it over to the height, and that looks like it is 8 feet. And that's it. Big idea coming out of today is to be able to figure out, given this question, what part of the quadratic function is it asking me to find? And then you're just going to use the graph to be able to find each and every one of those.